Day 9. Only 21 more days to go. Okay, so what is this? Ranger Goya is recording the number of sightings of different types of birds he sees in the state park in the graph below. Okay, so he's looking at birds and he sees 4 of the northern cardinal, 5 of the mountain. I'm not going to say the last word because I don't want to say it. The ruby-throated hummingbird, the other hummingbird, and then the woodpecker, it's 2, and the downy woodpecker as well. Okay, based on this result, what's the probability that the next type of bird Goya sees is a type of hummingbird? So here's his experiment, right? So he's doing well, I mean, it's not doing an experiment, but this is based on something that happened. So let's just add up all the birds that he saw. So far he saw, well, 4 over here, 5, 2, 6, 2, and 1. So if I add this 4 and 5, 4, 10, 15, 20. So he saw a total of 20 birds. And out of the 20 birds, how many were hummingbirds? Well, because it doesn't say a particular type of hummingbird as long as it's a hummingbird. So there are 2 types of hummingbirds. One was this guy here, which is 2, and the other one was here, which is 6. So out of the 20 birds, 8 were hummingbirds. So the probability, so the experimental probability was that he's in the experiment that 8 out of 20 birds that he saw was a hummingbird. So if we take that number and we want to see the probability that the next bird that he's going to see is a hummingbird, well, it's just 8 out of 20, right? So 8 out of 20 simplifies. 2 divided by 4 is 2, divided by 4 is 5, so it's 2/5. Is there 2/5? Yeah. All right. Page 1, the whole page for that one. Jeez. Can I make this bigger? Yes, I can. Okay, so Tanisha hit 40 golf shots and measured the distance of each shot. Here are the results. Okay, so I can say 5 of her shots were this distance, 11 of her shots were this distance, 190. So this one, 15 of her shots were 190 to 199, and that's a 9. And 9 shots were 200 to 209. Jeez. Nice. What's the probability, experimental probability that Tanisha hits a shot that is in the 100 and 189 yard range? So how many shots did she take? Well, 11 and 9 is 20, plus 5 is 25, plus 15. So she took 40 shots, and out of the 40 shots, how many were in this range? 11 out of 40. So probability of her hitting and her next shot at this range would be 11 out of 40. Okay. Not bad, lady. Not bad at all. Blah, blah, blah. The restaurant customers order a hamburger, a cheeseburger, or a chicken sandwich as their main dish. With any of those main dishes, you can order a side of French fry or salad. Side of French fry salad. Table shows the results placed by the last 50 customers. So let's just take a couple. 17 people order hamburger and French fries. 4 people order hamburger and salad. 11 people order cheeseburger with French fries, cheeseburger salad 6, and then chicken French fries 9, and chicken salad 3. How many people should say? 50? No, 50 customers. Okay, so based on the orders of the last 50 customers, what is the best estimate of the probability to the next customer? So the next person coming in, what is the probability that he will order a salad with the main dish? It doesn't say which main dish, but as long as the order was a salad. Well, there were 50, right? 50, customers. This experiment was based on the last 50 customers. So out of the last 50, how many ordered something with a salad? This guy, these guys, these guys, and these guys. So 6, 4 is 10, plus 13. So 13 out of the last 50 people orders a main dish with a salad. And if we obviously want to change this to a percent, because all of our multiple choices are in percent, we can divide that by, divide? So 13 divided by 50. That's one way of doing it. 13 divided by 50, and then multiplying that by 100 times 100, which is going to give us 26%. And because the answer says best estimate, we're gonna choose B. It's close enough. 4. Paula sat on her front porch and counted by color the cars that drove by. She recorded her results in the table below. So how many cars passed by her house? Let's add all those numbers first because I'm going to need it. 24 plus 14 plus 12 plus 30 plus 13. She counted 93 cars. So there were 93 cars that passed through her house. 23 were black, 14 blue, 12 red, 30 silver, and 13 white. Based on that data, the next car that's going to drive by, what's the probability that's going to be a black car? Well, on her experiment, how many were black? So 23 out of 93. She has a 23 out of 93 chance that the next car is going to be a black car. And did I add this wrong? Because is 23 going to 93? I think so. Let's simplify this. Wow, okay, so none of them. So it's 20. Let me add them again. 23 plus 14 plus 12 plus 30 plus 13 equals 92. So I got this one. So it's 92. And how many were black? 23. So maybe that simplifies. So 92 divided by 23 is 4. So that is definitely simplifies to divided by 23 is 1, divided by 23 is 4. So there's a 1/4 chance the next car is black. Ta-da. 5. Marbles were randomly drawn from a bag one by one. After each draw, the color was recorded, the marble was returned. So this is with replacement. So you take the marble and you put it back in the bag. So what's the experimental probability that a marble randomly drawn from the bag will be bred? Okay, so based on the experiment, well, how many, what do you call? Based on the experiment, how many trials did we do? How many times did it go into the bag? So let's add those. 8 and 2 is 10. 10 and 20 is 30, and 30, and this was done 100 times. Okay. So out of the 100 times, how many were red? How many were red? 25 out of 100. So the experimental probability, if the next marble is going to be bred, well, based on what she has done in the past 100 tries, 1/4, she has a 1/4 chance that the next marble is going to be red. Again, experimental. Okay. David is packing his lunch. The chart below shows choice for his lunch: sandwich, peanut butter and jelly or cheese. Drink, he has a choice of juice or milk. And snack, he has a cookie or a cake. Yikes. So basically you're asking, if you were to draw a tree diagram, which one is the correct one? Well, this doesn't look like a tree diagram, does it? That's gone. This also doesn't look like a tree diagram, so that's just based on aesthetics. I would just throw that out. And again, so it's either B or D. So let's look at D. So with D, I can get a peanut butter jelly, and with that, I can get juice. And with the juice, I can get cookie or cake. So I can have peanut butter and jelly, juice and cookie, peanut butter and jelly, juice and cake, or peanut butter and jelly with milk, with cookie, or peanut butter and jelly with milk and cake. So that's what do you call it? Another choice. So I can have a cheese sandwich with juice and then with cookie, etc. Here, what's wrong here? Oh yeah, with the juice, he forgot that you can have cake as well. So this should have been 2, and this should have been, in this case, cookie. So the one that's correct is letter D. Okay. The tree diagram shows all the possible outcomes for spinning the arrows of 2 different spinners. Based on the tree diagram, which 2 spinners could be a spinner X and Y? So which of the 2 spinners here was spun to get that particular diagram? Well, let me draw that spin. So let me draw both spinners. So I know it's spinner A, 6, 7, 8, and 9. So I need one spinner where it has 6, 7, 8, 9. And I need a second spinner. And in the second spinner, you can see that there's only 3 choices. So let me separate this into 3. And in that one, I have a star, I have a circle, and I have a diamond. So let's look for something that has that. So is it A? No, because the numbers should be all together. Is it B? No, because you're missing a 9. Is it C? No, because the numbers and the images are mixed. And D, look at that. Almost, oh, it's almost, actually, I did pretty good. Same as mine. Okay. Okay. Kelly tossed a coin 3 times. Which of the tree diagram represents all possible outcomes? Okay, so 3 coins, right? So this one is coin 1. This is coin 2. Where's coin 3? This is gone. This, I have no idea what this is. B, coin 1, coin 2, coin 3. That works. D, the top seems right, but what happens when you get tails? What can happen here? So that's gone. So this one is the one that's correct. 10. Maria has 3 spinners, shown below. Maria spins each spinner once to make a code consisting of 1 letter and 1 number and 2 letters. Using the spinners, how many different codes are possible? I see. So it's a code that has a number, a letter, and a letter. So if he spins this and he lands on 1, that's the first one. Spins this and lands on I. And if he spins this and lands on T, so your code would be 1IT, for example. So how many different codes can we make with these? Well, remember, there are 4 choices over here. Times, how many choices do we have over here? 1, 2, 3, 4, 5, 6 times 6. And then times, the last spinner has 3 choices, so we have 3. So remember, fundamental counting principle, we can multiply the number of choices in each one, and we get 24 times 3, which is 72, I think. 72 choices, letter D. 11. 3 coins are tossed. The tree diagram shows all the possible outcomes where H represents heads and T represents tails. What's the probability that Reggie will toss 2 tails or toss 2 or more heads? Well, let me do the sample space, bro. So I can get heads, heads, and heads, 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 and tail, heads, heads, and tails. I can get heads, tails, heads, heads, tails, heads, heads, tails, tails. I can get tails, heads, heads, tail, heads, heads. Tail, heads, tails, 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 heads, tail, tail, heads, and tail, tail, tail. So now it's much easier to look at it, right? So there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 different outcomes. And what's the probability that Reggie will toss 2 or more heads? So which of these has 2 or more heads? Well, there's 3 over here. There's 2 over here, so that counts. There's 2 over here, that counts. There's 2 over here, that counts. There's 2, no. So out of all the 8 possible outcomes, 4 of them has 2 or more heads, right? So this has 3, this has 2, this has 2, and that one has 2. And nothing else has 2 or more. So 4 out of 8, or 1/2. And I love that this one, they did not simplify. Darnay is planning to decorate a room. She will choose 1 color of paint, 1 color of carpet, and 1 pattern for the wallpaper. The colors and the patterns she will choose from are shown below. How many different combinations of 1 paint, 1 carpet color, and 1 wallpaper pattern? This is no different than the key code we did a couple of problems ago. So for paint, there are 3 different colors. Carpets, there's 2 different colors. Wallpaper, there's 2 different colors. So just multiply them up and you get 12. 12 has stores selling t-shirts. T-shirts are available in red, blue, and white. Shirts of each color are available in sizes small, medium, and extra large. Okay, so here's a little tree diagram. Looks right. There's a red. I can get a red in the small, red in the medium, red in the large, red in the extra large, and so forth and so forth. Amy will randomly select one shirt from a shelf. If the shelf contains equal numbers of shirts in each color and size combination, what's the probability that she will select a large shirt? Well, how many different possible shirts are here at the wall? There's red and small, red and medium, red and large, red and extra large, blue and small, blah, blah. So there's 4 shirts, plus another 4, plus another 4. So there's 12 different shirts. And she wants to select without looking a large shirt. So how many of those are large? Well, one here, a blue, oops. You can get a red, so you can get a red on the large, you can get a blue on the large, and you can get a white on the large. So there's 3 different shirts out of 12 that are large. The probability of her selecting a t-shirt that's large, regardless of color, because they didn't mention any color, is 3/12 or 1/4. Ty plays a game using 2 spinners. Each spinner is divided into 3 equal sections of equal size as shown below. She will spin the arrow on each spinner one at a time. The organized list shows all possible combinations. Okay, she can get a red in the 1, red in the 2, red in the 3, green in 1, green in 2, green in 3. Yeah, okay, so that sounds fair. What's the probability that the arrow on spinner M will land on green, and the spinner N will land on a section with an odd number? So what's the probability of getting a green with an odd number? Well, a green was an odd number, that's here, 1 is odd. A green was another odd number, that's here. So probability of getting that is 2 out of, and how many choices? 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 out of 9. 14, the tree diagram shows all the combinations that can occur when a fair coin is tossed 3 times. So you toss a coin 3 times. What's the probability that the person who tosses a coin 3 times will get head twice and tails once in any order? So as long as you get 2 heads and 1 tail. So how many has 2 heads and 1 tail as well? Heads, heads. So there's how many total outcomes? There's 1, right? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 different things that can happen. I'm just going to erase this because it's a little messy. So out of the 8, which of those 8 have tails, 2 heads, and 1 tails? Well, this has heads. Sorry, let me write this out. 2 heads and 1 tail. So how many of these have 2 heads and 1 tails? Not that one. Not this one. This one has heads, tails, heads. Heads, tails, heads. That has 2 heads and 1 tail. Heads, tails, tails. No. Tails, heads, heads. Tails, heads, and heads, right? Tails, heads, and heads. That's another one that has 2 heads and a tail. And tails, heads, tail, tails, tails, heads, tail, tails, tails. So out of the 8, 2 of them have 2 heads and 1 tail. So 2/8 or 1/4. Uh-oh, I got it wrong. I want 2 heads and 1 tail in any order. 2 heads, 1, 2. Oh, I'm sorry. There's 3. It's because it's heads, heads, tails. So this one's heads, heads, tails. Heads, tails, heads. Heads, tails, heads. And then there's one more down here. Tails, heads, heads, tails, heads, heads. So 3 possible outcomes have 2 heads and 1 tail. So 3 out of 8. So the correct answer, I believe, was A. Yeah. No. C. 3/8. Okay. Tree diagram again. This is the choices when you order thin crust. Choices of meat, pepperoni, extra cheese or toppings, pepperoni, extra cheese and sausage, and the last choices you have mushrooms, olives, and onions. So if each pizza order is equally likely, what is the probability that an order will be a thin crust with pepperoni and mushrooms? So look, that's how many thin crust, pepperoni, and mushrooms Will I have thin crust, pepperoni, and mushrooms? So 1. Is there anything else that will give me a thin crust, pepperoni, and mushrooms? No. So 1 out of the how many total possible pizzas that we can make? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 out of 18. 1 out of 18 will have thin crust, pepperoni, and mushrooms. That's it. Really? Okay.